Welcome. Today we're diving into the basics of power systems. Power systems are the backbone of modern society, supplying electricity to homes, businesses, and industries. Understanding how these systems are structured and how electricity is generated, distributed, and billed is essential for anyone interested in energy or engineering. In this video, we'll break down the main components of a power system, explore different types of power stations, look at how loads are managed, and finally discuss how tariffs are structured. Let's start by looking at the overall structure of a power system. Typical power system is divided into three main parts: generation, transmission, and distribution. Generation is where electricity is produced, usually at power stations. Transmission involves moving this electricity over long distances using high-voltage lines. Finally, distribution brings electricity to homes and businesses at usable voltage levels. Each part plays a crucial role in ensuring that electricity is available whenever and wherever it's needed. This structure helps maintain efficiency, reliability, and safety throughout the entire process. Power stations, also known as power plants, are facilities where various forms of energy are converted into electrical power. There are several types of power stations, each using different resources and technologies. The most common types include thermal coal-fired, hydroelectric, wind, solar, and nuclear power stations. Each type has its own working principle and unique advantages, which we'll explore in the next few scenes. Start with thermal power stations. These plants use coal or other fuels to generate heat. The heat is used to produce steam from water, and this steam turns a turbine connected to a generator. The generator then produces electricity. The process can be summarized as: coal is burned to create heat, water is converted to steam spins the turbine, and the turbine drives the generator to produce electricity. Thermal power stations are widely used due to their ability to generate large amounts of electricity. Hydroelectric power stations harness the energy of falling or flowing water. Water is directed onto turbines, causing them to spin. These turbines are connected to generators, which convert the mechanical energy into electrical energy. The process is clean and renewable, making hydroelectric power a popular choice in many regions. The basic flow is: water moves the turbine spins the generator, and electricity is produced. Hydroelectric plants are especially valuable for their ability to quickly adjust output to meet demand. And power stations use the kinetic energy of wind to generate electricity. Large blades mounted on a rotor are turned by the wind, which spins a shaft connected to a generator. As the wind blows, the blades rotate and the generator produces electricity. Wind power is a sustainable and environmentally friendly option, especially in areas with consistent wind patterns. The process is straightforward. Wind turns the blades spin the generator, and electricity is generated. Solar power stations capture energy from sunlight. There are two main types: photovoltaic PV systems, which convert sunlight directly into electricity using solar cells, and solar thermal systems, which use sunlight to heat a fluid and produce steam to turn a turbine. Both methods are clean and renewable, with PV systems being more common for direct electricity generation. Solar power is increasingly popular as technology improves and costs decrease. Nuclear power stations use nuclear fuel, such as uranium or plutonium, to generate heat through a process called nuclear fission. The heat produced is used to create steam, which turns turbines connected to generators. Nuclear power is capable of producing large amounts of electricity with low greenhouse gas emissions, but it requires careful management of radioactive materials and safety protocols. Load curve shows how the demand for electricity varies over time at a power station. By analyzing load curves, operators can understand when demand is highest and lowest, helping them plan generation and distribution more efficiently. The daily load curve, for example, reveals how demand changes throughout the day, while the area under the curve indicates the total units of electricity generated. The highest point on the curve represents the peak demand. Connected load refers to the total rated capacity of all electrical devices connected to the power system. However, not all devices are used at the same time. Maximum demand is the highest level of power required by the system during a specific period. Typically, maximum demand is less than the connected load, since consumers rarely use all their devices simultaneously. Understanding these concepts helps in designing and operating efficient power systems. Demand factor is the ratio of maximum demand to the connected load. It's always less than 1 because not all connected devices are used at once. For example, if the maximum demand is 80 megawatts and the connected load is 100 megawatts, the demand factor is 0.8. This factor helps utilities understand how efficiently the connected load is being used and aids in system planning. Average load is the average power demand over a specific period, such as a day, month, or year. The load factor is the ratio of average load to maximum demand. A higher load factor indicates a more consistent and efficient use of the power system, which can reduce costs and improve reliability. Utilities aim for a high load factor to optimize their operations. Diversity factor is the ratio of the sum of individual maximum demands to the maximum demand on the power station. It's always greater than 1 because not all consumers reach their peak demand at the same time. A higher diversity factor means lower generation costs, as the system can be designed for a lower overall peak. This is a key concept in efficient power system design. Plant capacity factor is the ratio of actual energy produced to the maximum possible energy that could have been produced during a given period. The plant use factor is similar, focusing on the ratio of kilowatt-hours generated to the product of plant capacity and operating hours. Both factors help measure how effectively a power plant is being utilized, guiding decisions on maintenance and upgrades. Load duration curve arranges the elements of a load curve in descending order of magnitude. This curve provides a clearer picture of how often certain demand levels occur, making it easier to plan for base load and peak load requirements. The area under the load duration curve equals the area under the original load curve, representing total energy consumption over the period. Domestic load refers to household electricity consumption. This includes appliances like TVs, washing machines, air conditioners, ovens, and refrigerators. Domestic loads are typically variable depending on the time of day and the habits of the residents. Understanding domestic load patterns helps utilities manage supply and demand more effectively. Commercial load includes the electricity used by shops, restaurants, offices, and other businesses. This load often consists of lighting, fans, air conditioning, and various electrical appliances. Commercial loads can be significant, especially in urban areas, and tend to peak during business hours. Managing commercial loads is crucial for maintaining grid stability. Industrial load comes from factories and manufacturing plants. The magnitude of industrial load depends on the type and size of the industry, ranging from small workshops to large factories. Industrial loads are often steady and substantial, with power demands ranging from 25 kW to 500 kW or more. Efficient management of industrial loads is vital for economic growth and system reliability. Besides domestic, commercial, and industrial loads, there are municipal, agricultural, and traction loads. Municipal loads include street lighting and water pumps. Agricultural loads are mainly for irrigation systems, while traction loads refer to electric trains and railway systems. Each type of load has unique characteristics and impacts the overall power system differently. Base load is the minimum level of demand that occurs almost continuously throughout the day. Peak load refers to the highest demand periods which occur over and above the base load. Power stations must be designed to handle both base and peak loads efficiently. Managing these loads ensures a stable and reliable electricity supply for all consumers. Tariff refers to the rate at which electrical energy is supplied to consumers. The main objectives of a good tariff structure are simplicity, fairness, and encouraging efficient energy use. There are several types of tariffs, including simple uniform, block rate, two-part, power factor, and time-of-day tariffs. Each type has its own advantages and is designed to suit different consumer needs and promote optimal use of the power system. Let's briefly look at the main types of tariffs. Simple or uniform tariffs charge a constant rate per unit of energy. Block rate tariffs offer reduced rates for higher usage blocks. Two-part tariffs split charges into fixed and variable components. Power factor tariffs penalize low power factor usage, while time-of-day tariffs vary rates based on when electricity is used. Each type is tailored to balance fairness, efficiency, and system stability. Time-of-day tariffs are designed to encourage consumers to use electricity during off-peak hours, reducing strain on the grid during peak times. This not only helps balance supply and demand but also promotes energy efficiency and cost savings. For large consumers such as industries and even for smaller users, time-of-day tariffs can lead to significant savings and a more stable power system. Summary: understanding the basics of power systems, from generation to distribution, and the various types of loads and tariffs, is crucial for efficient energy management. Each component and concept plays a vital role in ensuring reliable, affordable, and sustainable electricity for everyone. As technology evolves, power systems and tariff structures will continue to adapt, making energy use smarter and more efficient. Thanks for watching, and stay curious about the world of energy.